All right, good afternoon, everybody. Welcome back from the loan break. I'm so sorry there's a little bit of connection issues here, so we apologize for getting started so late. I won't babble too long. I just want to go ahead, and if you guys haven't had a chance to do so, if you guys can just give us a thumbs up, if you guys can hear us okay. Here's somebody saying hearing clicks. You might hear a few clicks, but if you guys can just give us a thumbs up to make sure the sound is okay, that would be perfect, and we'll go ahead and get started here. All right, perfect. I'm going to go ahead and turn it over to Daniel. Daniel, whenever you are ready, you can feel free to get started.
Yeah, thanks everyone for listening to me today. So we're running a little bit behind. I'll try to go through a couple of things a little bit faster to make sure we still leave time for some questions at the end. But my name's Daniel Fay. I'm a cloud solution architect here at Microsoft, and I primarily specialize in our advanced analytics and AI offerings. So without further ado, let's get started. I'll be talking today about Azure Machine Learning Service. So we have a different suite of kind of Azure AI products. We have our apps and agents, our machine learning, which is what I'll be touching on today, as well as our knowledge mining, just to give a brief overview of kind of the different things that we offer. So what we did here at Microsoft is we thought about the different building blocks for a typical data science project. So as you can see here, we typically take a data source from somewhere. We want to build and train our models. Within that training, we want to do hyperparameter tuning. Within that, we may want to do that with several different models. We may even want to think about kind of creating a lot of those steps to put into a reusable pipeline. And then eventually, once we kind of have that process laid out, we would then want to deploy our model. And of course, through this entire life cycle of this development process, we want kind of another place to kind of isolate our production from our development environment. So we also offer that within our Azure Machine Learning Service. So after we thought about all this stuff, we kind of came up with a single unified product. And what that is what we call Azure Machine Learning Service. So it's a set of different Azure cloud services located in one singular workspace that you can either interact with through the graphical user interface in the portal or through a Python SDK. What this enables you to do is just a lot of the things I mentioned before. So we can prepare our data, we can build and train our models. We have some automatic versioning in there to help manage our models. We can track different experiments and metrics and statistics about those experiments, as well as eventually deploy the models once we're satisfied with them. So it's quite a flexible framework, so you can really build and train your models anywhere. So the only limitation we have is you need to be able to connect to the Azure Machine Learning workspace using the Python SDK. So that's the only limitation. Anywhere you can write Python and have an internet access, you can use our Azure Machine Learning Service. So whether that be through a visual code, and we even have a machine learning extension that creates some of those connections a little bit easier for you, eliminates some of the code writing. Any notebook, a Jupyter notebook works fine, or any Python IDE that you're currently familiar with or comfortable with using. We also offer a command line interface to connect as well. So within that, that's how you actually connect to this service. And then from there, you can do different things, right? So you can train your model on your local machine, simply use it to store metrics and experiments. You can train your models on some PaaS computes that we offer within the workspace. So I'll touch on those in a little bit more. And then, of course, you can scale these processes out both vertically and horizontally, whether that be through increasing a VM size, adding more VMs, or maybe moving to a Spark framework like Databricks or something like that. So finally, once we've kind of gone through this build and training of our models, we want to think about deploying. So the way we deploy models is we're actually going to provide a configuration for our inference container. This is going to be a Docker container that's located in our container registry within Azure. And once we do that, we can actually deploy it in a few different places. So we can do on-prem deployment. If this is particularly an IoT case, we can look at an edge device. An Azure container instance, which is kind of specialized for development of models, an AKS cluster, which really specializes in production version of models, or either some of the other things like our IoT accelerated targets or even some FPGAs. if inferencing time is a concern. So kind of why am I talking about this today? So the idea behind this whole framework is we want to have our data scientists and analysts spending the time on what they should be spending the time on, and that is exploring their data, building models, looking at experiments, and deploying and managing those models. We don't want to spend a lot of time creating organizational structure for different events or models. So this kind of creates one singular workspace where all this stuff is located. Within this workspace, we actually have a lot of different offerings as well, and I'll touch on these more in a little bit, but just to give you guys a high-level overview, we have something called automated machine learning, which kind of takes care of some of the training process and building models for you. We have different managed computes, simple deployment offerings like I just touched on. We have built-in kind of tracking and versioning within the workspace, but additionally to that, we can actually connect it to Azure DevOps. And like I mentioned before, we're kind of tool agnostic as anywhere you can run a Python SDK. So let's touch on some of the little bit more specifics here. So we have automated machine learning. So what that looks like here is, let's say we're trying to do a model and we say, how much do we want to predict how much a car is worth. So typically, a typical way of going through this is we're actually going to go through, maybe do some feature selection. We're going to choose our model. We're going to have to select some hyperparameters. Eventually we get a model accuracy. So we can see, maybe through this process, we got a 30%. Not very good. So how do we kind of automate some of this process so that, we don't need to manually be doing a lot of these things yourself? So what AutoML is going to do is actually going to iterate through a lot of these different algorithms and hyperparameters to identify a more optimized model. So it comes with a list of algorithms. It also has some pre-processing enablement, so it'll actually scale some features, and in some cases do some feature engineering as well. And then lastly, it's going to select an algorithm to train your model on. It's then going to go through a bunch of different iterations to find out which is the best model, and it kind of has a decision tree-like structure from based on how it trained the first model, the subsequent models to go after. So you can see here, you might typically how the experiment's going to work is you're going to give it your training data. You're going to define goals. So let's say maybe that is we want to optimize in a classification sense, maybe an AUC metric or an F1 score. And so that's what it's actually going to be used to evaluate the models and choose the next one. And then we may want to apply some constraints to the model. So for instance, if we're certain that we don't want to look into certain models, we can blacklist certain ones that are on the list. So at the end output here is you get a list of models trained by the algorithm, and then obviously typically most people are interested in the highest performing based on that metric constraint. So you can see here I trained several different models, and you may take the 95% one. So now a lot of our customers also ask, hey, we built this model using your automated machine learning, but we want to figure out what were the actual hyperparameters in the model, as well as maybe how the features impacted that model. So we didn't want to just leave our customers with kind of a black box. So we also enabled some model explainability features. So if you actually go into the experiments, and I'll go through a demo through the portal here briefly, but you can see that we'll have a lot of pre-made graphs, one of those being feature importance. And of course, this is a common ask for a lot of people, right? Is what feature is impacting my target variable the most? So you can actually see here, in our 95% model, the price of the car, the mileage pays quite a big factor into the price of the car, which makes sense. Additionally to some of these other things behind feature importance, we can actually print out all the parameters and the particular model that was generated. And so if you'd like, you could actually back engineer that model and let's say like sklearn or something, or you can actually download the model as a pickle file and use it wherever you'd like. Okay, next, let's discuss some of the managed compute within our Azure Machine Learning workspace. So within here, we have various different computes ranging from VMs, to an Azure Kubernetes cluster, to another thing we call Azure Machine Learning Compute, which is kind of a special compute optimized for essentially machine learning pipelines and particularly training of your models. But the way these works is when we submit through the workspace as an experiment, we actually containerize that process. So it's typically a Python script or an R script or what have you, and you can submit that to the compute, and it's going to go through and actually containerize that and run that job. Within that, we have a few different things that come with the managed compute. So you can actually schedule jobs. Depending on your compute, you can distribute your processes and data. You can easily scale your resources. It's secure, and we also have things for handling failures within those experiments. So this is touching on a lot of the things I mentioned before, but these are the kind of highlighting things that you want to think about when utilizing the PaaS service. These are some of the things you will not have to worry about when using the managed compute within the machine learning workspace. And just to touch on that, we do offer a variety of infrastructures. So we can go anywhere from a general CPU to a GPU for more deep learning models like TensorFlow, or we can even use FPGAs where you may want to customize for even a higher performance. Okay, so let's get into the development operations for machine learning. So as I mentioned before, a typical data science pipeline, we want to train and test our models. We want to register those models. After we register them, we may want to build an image and save that image for future use and eventually deploy that. And within this kind of loop, we want to have different versionings and registries for our different scripts, our models, our images, and our deployments. So actually within the machine learning service, it's actually going to create versions for you within the service automatically. But as I mentioned before, if you have your code located on like a GitHub repo or through Git within Azure DevOps, you can absolutely connect this Azure Machine Learning Service to that Azure DevOps. And for instance, if you had your code located in a GitHub repo and someone were to commit a new script to overwrite an old one, that could automatically trigger a pipeline run within Azure DevOps. So we kind of seamlessly integrate with that, and we actually call that ML Ops. Model management in detail. So we enable the DevOps for the creating and retraining of the model. So we have versioning through every single model that's trained, and this allows you to do the continuous integration, continuous deployment. In addition to that, we actually have quite a number of ways to monitor the deployed models, whether it be through data capturization and looking at data drift that the web service endpoint is receiving, or you can actually go into our app insights and monitor load and balance based on what's being requested. The next thing we have is our experimentation. So I'll get into this a little bit more detail if this is still kind of sounding vague, but the way you submit things within our workspace, for instance, to like train a model, is you kind of wrap it into an experiment. So within each experiment, we also provide tracking. So you can kind of run and log metrics within the experiment that are then saved in the workspace for easy viewing. You can create custom visualizations within the experiment. So for instance, if you wanted to have a leaderboard of different models, maybe you have an accuracy metric plus, a runtime. So you can kind of evaluate them on different criteria. And then of course, within that experiment, maybe you have a specific set of hyperparameter grid search that you're doing from one range to another. After training one model, you say, hey, I want to do kind of a more refined hyperparameter search. You could submit another experiment. Of course, that is all tracked as well. Okay, I know I'm going through a lot of this quick, but we'll touch on this in a demo in just a little bit. So what are Azure Machine Learning pipelines? It's taking all those steps that I previously just discussed and actually packaging them into a pipeline. So if you're familiar with like an sklearn pipeline, it's very similar. You're essentially just creating distinct steps within a workflow and appending those to a list. And then that is read and published to your machine learning workspace as a pipeline. From there, you can do lots of different things with it. But a typical data pipeline is going to, may ingest your data will be step one, maybe prepare your data. So that's going to be some of your transformations, normalization, potentially splitting your data between training and test. Our next step in our pipeline could be building and then training our model. Then we have maybe another step to select a model based on a criteria, deploy that model, and then potentially score some data from it. So that would be like a typical pipeline. One of the nifty features here is you can kind of see through this. We'll actually go through the different steps. And if there is a testing error, it'll output that in the specific place in the code, as you may expect. You can go in there into that Python script or however you built the pipeline, change the code, hopefully addressing the error. If you were then just to rerun the pipeline, it's just then going to restart the pipeline from that particular step. Hopefully the error is resolved and move through the pipeline. So it enables you to kind of publish into this reusable workflow, but you don't necessarily are restricted to running the whole pipeline every single time. We have built-in ways to actually resolve errors with saving time by not running the entire pipeline. So what are kind of the advantage of this? You can schedule runs. So you can do an hourly or event-based run within a pipeline, as well as it is just an API that you can call. So if you were building like a web application and you needed to have some logic, and then within that logic, trigger an Azure Machine Learning pipeline, all you need to do is simply call that API and trigger the run. Just like a lot of the other things within our Azure Machine Learning workspace, it also enables tracking and versioning, reusability, so you can download this as a template or simply save it and being reused for other people within that workspace. And then within each of those steps, we can utilize many different computes. So you're not limited to one specific compute for a pipeline. It's actually how you configure each step in the pipeline. So we're getting close to the end of my slides, but so just to touch on some things again here, we support a lot of different frameworks, and at the end of the day, anywhere you can write Python, you can utilize Azure Machine Learning Workspace. But of course, we have some native configurations within the SDK for TensorFlow, PyTorch, sklearn, Keras. And then if you're interested in doing some distributed training using TensorFlow or Keras, we also offer some Horovod integration, so you're easily able to do some of that distributed training as well. We also offer Onyx, which is a new offering, and that is also available within the workspace. And lastly, so I just want to hit this point home. You can really access this through anywhere. So whether you are using PyCharm or a Jupyter Notebook on your local computer, or you're in a data science VM, you can use the Azure Machine Learning Workspace. You can use it in Databricks because you can write Python. So it's very flexible in that regard. Okay, and just to wrap up, so this is kind of an overview of what our whole machine learning on Azure looks like. So at the top here, we didn't touch on these, but those are some of our cognitive services that can be integrated, our familiar data science tools, our popular frameworks, our product services. So we didn't touch on Databricks too much, but that can leverage Azure Machine Learning, and then of course the different compute structures. Okay, so now I'm going to jump into a quick demo here. So I hope everyone can still see my screen here. And so what we have here, this is the portal. So if you were to go in here and create a resource, you need to associate with a resource group, but you could type in Machine Learning Workspace, Machine Learning Service Workspace, and you go ahead and create. Once you've created that, you then have something that might look like this. And so what I want you to key on in here is this like left panel. So this is kind of your navigation bar. So I'll be touching on a handful of these things, but here we kind of have our automated machine learning. You can do this through this tab here, which opens up a GUI to do the automated machine learning, but of course you can also do this through our Python SDK. We have notebook VMs. And so what these are is these are actually data science VMs that come with a pre-configured to your Azure Machine Learning Workspace, and then this nifty kind of interface here that easily loads a Jupyter Notebook or Jupyter Lab in this case. And so within this, I have some code written here that I'll walk you guys through how to use, how to go through a basic training of a model and deployment. So we're going to import our packages to start. And then within this notebook VM, it actually comes already configured with this configurations file. So typically, if you want to connect to your workspace, you're going to need to pass in like the subscription ID, the resource group, the workspace name. But because this was created within our Azure Machine Learning Workspace, it has the configuration file already loaded. So you can simply just say workspace from config. We've now loaded in our workspace. Now we're going to create an empty experiment to eventually submit something to. So we're simply giving it a name. We're passing experiment, the workspace that experiment is going to take place in, and that name that we just specified there. Within the workspace, you can actually associate different storage accounts with the workspace for easy access. You don't have to pass credentials. So I previously registered a data store, which is just a blob storage account. And so all I need to do is, once I do that, is again pass this workspace and the data store name. I then save the connections to that blob store as DS. So then the next part of this is we want to set up the compute target for wherever we're actually going to train this model. So in this case, we're going to be utilizing AML compute. To give you guys a little bit of background on what that looks like, let me take you back to the portal. So if we go to compute here, it's very easy to create a new compute within your Azure Machine Learning Workspace. So if you were to just say add compute, you'd give it a name, then you have a list here. So machine learning compute, Kubernetes service, VM, etc. So here you choose your virtual machine size. So what AML compute is, it is just a set of VMs that will scale up and down as the load increases or decreases. So it doesn't actually distribute a single training process. These need to be discrete experiments or processes that it's able to distribute. So for instance, if I were to be running an experiment using sklearn to train a single model, and I submit that to AML compute, and I have the maximum number of nodes 0, and let's just say 8, it's going to spin up one node, run that experiment. If while that experiment is still running, another member of my team submits a similar experiment, it's just going to then provision another node to 2 nodes and run that experiment. Once any of those experiments are finished, it automatically scales back down to whatever your minimum number of nodes is after the idle second time. And if you're familiar with Databricks, it's a similar auto-scaling structure. Okay, so we are setting that as a compute target. We then need to pass the run configuration for our training of our model. So the first thing we need to do is let it know that, hey, we're going to be running Python. So this is a Python run configuration. We give it the compute target that we just set previously. We want to let it know that we're going to be using a template for a typical Docker-enabled environment. And then we're going to begin loading some dependencies here within Conda packages. We're then going to save that into our Conda run environment Python Conda dependencies. So at this point, this variable here, Conda run configuration, is now set for our training experiment. So in this case, I'm just loading our xtrain, ytrain, xtest, ytest from our registered data store. In the case of submitting on AML compute, we actually do have a limitation that our data needs to be in this tabular format. So you need to load it in using this dataset package. I found the easiest way is to split your training into ytrain, ytest as part of an ETL process, save that data into a blob store wherever you have your data located, and then load it in with the code listed here. So now that we have our training data and our run configuration set up, we're ready to set the configuration for our experiment. In this case, we'll be running an automated machine learning experiment. So kind of some of those constraints and things that I touched on earlier, you'll actually see here. So we're running a classification task. We're going to have an errors log that is located to auto_ml_errors.log. Our primary metric, AUC weighted. Our cross-validation, so this is how we're splitting our data and validating it within each of those models. Whether or not we want to pre-process any of the data. Our iteration timeout minutes is actually the amount of time it can spend training a single model. If after 10 minutes that model is not trained, it's simply going to move on to the next one. Iterations, in this case, iterations is just the number of algorithms to try. I'm sorry, that can be a bit misleading. It's not actually the discrete number of algorithms, but it's the discrete number of combinations of either scaling the algorithm and the hyperparameters for that algorithm. So that can constitute an iteration. Our run configuration, so this is what we just set before, our max concurrent iteration. So this is a nifty thing that since we're submitting this to AML Compute, and AutoML has a built-in way of identifying AutoML Compute, we can actually just specify this parameter here to say, hey, scale out our AutoML Compute to 6 nodes and train 6 concurrent models all at the same time. So if we were running 30 iterations, we would only need to submit essentially 5 different jobs, each containing 6 models at a time. We then pass our X train and Y train data, as you might expect. I have this commented out here, but you can actually blacklist models. So by default, it's going to select the models for you based on the entire list given. But if you were to say, hey, I'm not interested in a handful of models, or I specifically want to direct it to a subset of them, you can actually blacklist the models you don't want. And you might be asking yourself, why don't we have like a whitelist? And we do, and the product group is working on it. It currently has some issues right now. So the best way to actually do that is by using the blacklisting feature. But if you were, I would think by the beginning of next year, the whitelist feature would be capable of doing something similar. So once we set up our configuration here, then we simply just need to submit it to the experiment. So we saved our experiment as experiment before. We're going to submit this configuration that we just set. And show output true is just going to print this stuff out that you see here. So I don't want to spend too much time here, but this is what you would see if it prints out. And you can see the duration and then the metric, and it's constantly tracking each algorithm. Let me show you what this actually looks like if you were to look in the Azure Machine Learning Workspace. So we went through, we ran that code, and now we want to see, hey, what do those different things look like? So if we were to actually go in here and look at an experiment, so this is one I ran earlier, you actually see 2 run numbers. One run is to kind of coordinate the distribution across the different VMs for the training of the models. And then the first run is the actual training of all the models. So if you were to click into here, you have a pretty cool little dashboard, I would say, and metric logging. So this first one here is just the iteration number, and this orange line is tracking the highest performing model. One thing to note is the last iteration is always, unless specified in the configuration not to, is going to be an ensemble model, which almost always is going to perform the best in comparison to the others. So if we were to go down here, for instance, you can see the list of all the models that were trained, as well as the scaling procedure that was happened, the metric we're tracking, whether it completed or failed, when it created, the duration, etc. The cool thing here is if we were to say, hey, we like the voting ensemble, this is our highest performing model based on this metric, and we say we want to dig a little bit deeper into this, you can actually click into this specific model. And it's actually going to populate a lot of graphs for you, as well as list out a handful of other metrics that are automatically tracked. And so if you were to scroll down here, you can see like an RLC curve, a gain curve, a calibration curve, that feature importance curve I was showing you guys earlier, as well as a confusion matrix on that training data you submitted. So it's pretty cool that you can actually create a lot of this stuff yourself. You can actually also create some custom dashboards if you'd like in here as well. Within this experiment too, you can go to outputs. So you can actually see that we have like a dependency file here that's printed out, as well as the actual pickle file. So if you wanted to simply download that, you could simply download the file here. Okay, so now I've shown you what that looks like. If you wanted to return that model, you can simply say remote run, get output. That's going to return our best run and the fitted model. Here, we're just going through a confusion matrix on our test set. And here's something that a lot of our customers ask for, like I mentioned before, the model explainability. So in this particular case, we're using an ensemble model. So we want to know what's actually part of that ensemble model and what are the weights associated with each one of those algorithms. So you can go through here. This code is a standard code that you can copy and paste from our documentation. It's going to print out all the information about whatever fitted model you pass it. So in this case, the case of our voting ensemble, where it looks like we have about, this is 9, looks like 8 different models that are within this, and we have our weights for each one of those models within the ensemble. And if we're to scroll down further here, you can actually see the exact details of each one of those models. So it used a robust scaler to scale the data, then a light GVM classifier, and here are the hyperparameters that it used to train that model. So if you'd like, you'd actually go through and back engineer some of this stuff. And it's going to print out all the information on each one of the models here. This is just printing out the feature importance. You can also see that in the graph I showed you in the experiment. This is code to show you a lot of those figures that were already displayed in the experiment I already showed you. And then lastly, kind of the last step here is, oh, okay, we like the model, we've evaluated it at this point, let's register it. So you would run this code. You're simply just going to pass it the model name, description, and tags. It's then going to automatically register this within our model registry within our workspace. So if you were to click on models, you could then see the model here. You can see I've done it a couple of times, so it automatically tracks the versioning of the model. So if you want to go back to a previous version of the model, that's very easy. And then I just want to point out, I'll show you how to do this through code in just a sec, but if you wanted to from here just deploy the model through a user interface, you could create the image. You just need to pass a scoring and environment file. It creates an image, and then then you can deploy it by just selecting a compute target to deploy on. Okay, so now let's get into the deployment. So similarly, before we're going to connect to our workspace, we're going to retrieve the model from our model registry that we're interested in deploying. In this case, we're just grabbing the dependencies from that particular run so we can pass that to the inference configuration. We create our environment file here. We write a scoring file for the container for our web service. And this is pretty much a template for this. So all you really need to do is just replace this model name with your own model in your workspace, and this should work to take in a certain JSON format and return a specific JSON format. We then pass our runtime, again being Python, this scoring file we just created, and that environment file to this inference config parameter. This is kind of similar to our conda run config previously. We then select our compute target. In this case, we're going to deploy onto an AKS cluster. We set the deployment configuration within that AKS cluster. And then finally, we deploy that by passing the workspace, the name of that web service, the model, the inference config, deployment config, and AKS target. Once that's done and you run this code, you'll see some stuff printed out here. And eventually you should hopefully have something that says, username is completed successfully. That means your model is completed and deployed. And then if you wanted to simply test that web service, here's some sample code to do that. So in this case, we call the web service based on this, and we see a result of 1. I think in this case, we're predicting if someone will default on their next credit card payment. So in this case, we will predict, yes, they will. So this is basically a basic overview of everything else. I think I'd like to turn it over to some questions at this point. I don't know if anyone's, let me look through some of the questions here. Why Python and not F? I'm not sure what that means, Alan. Okay, if there's not any more questions, then I can dig into some more examples here. Okay, so within this, we can also do a lot of these things through a graphical user interface. You're not limited to just code. So I want to show you guys how easy it is to actually build an automated machine learning experiment within the graphical user interface. So if you wanted to do it here, so when we say create experiment, give it whatever experiment test, crowdcast. You'd select the compute that you'd actually be doing the training on. We then need to upload some data. So in this case, it can connect to some already preloaded data sets, or you can actually, upload your own from your own local machine. So in this case, I'll upload this credit card data. Okay, and here we are. You select that data source. You want to let it know, hey, we're going to be doing a classification task, which is correct in this sense. We want to know the target column name. I believe in this data set, we have it as the very end. My God. Okay. So that's our target column. This is our Y. And then under our advanced settings, we might want to set our primary metrics. So we have some different ones here. I don't know. So let's just say AUC weighted. So this is actually a metric threshold to let it know when to not even return a specific model if it's under a certain threshold. Again, the maximum number of iterations. So in this case, this would train 100 different models, maxing them out at 60 minutes per model. If it were to go under that, it times out. We're going to turn on pre-processing. Validation type, we have a few different options. K-fold cross-validation is the most widely used. If you want to set that to a different fold number, you simply can here. And then because we're using AML compute, we can scale up to different number of concurrent iterations depending on the maximum number of nodes in that AML compute. And then lastly here, like I mentioned before in the blacklisting algorithms, you could actually blacklist some algorithms here. And so, let's just say we want to just train 5. And let's just do 3, make this a little bit faster. And then you just click start. So it's actually gonna, from there, you're essentially done. And what it's gonna go through this experiment. And what you'll be left with at the end here is an experiment listed here. So this one's running, as you can see, but we wanted to look at like a completed experiment. It's very similar to kind of what I submitted through the SDK. So you can go through here, you'll see all your different models. You can simply download those models right here. And then we have easy deployment. So if you said, I want to deploy the best model, you can simply click that. It's actually going to auto-generate the scoring and environment script directly from that particular iteration run. And then you can click deploy and you're done. So it's probably the easiest way, I would say, for someone without a strict data science background to actually begin building and testing out models. And it's much more robust than some of the other offerings we have, such as our visual interface, which is also, as you might know, Machine Learning Studio. So that's actually the same thing. Okay, that's a good question, Andrew. Let me touch on that. So, okay, I apologize if it was difficult to follow along with the code. What I can do here is there's a great GitHub repo that's going to have notebooks on how to get started with all this stuff. So let me send this within the chat window. I apologize if you can't see, but on the bottom of this main page, it's going to have a list of different repos with links. And if you were to follow those in order, you're going to get a very good overview of how to use this using the Python SDK. So please look into that GitHub repo. I think it can answer quite a lot of your questions. And that's going to touch on anything from training on your local to training on remote compute to deep learning to using AutoML to building pipelines. So there's quite a lot in that repo to go over. Okay. Lastly, since we have a little bit more time and I'm not seeing any other questions. Okay, thank you. You're welcome. Let me touch on our visual interface really quickly. So similar to this kind of automated ML, we have a way of building machine learning algorithms completely through a graphical user interface. And this is more for a citizen data scientist. So there are some limitations in terms of the algorithms you can use. But in terms of building out a pipeline and creating a predictive experiment and then deploying that, it's quite powerful for people just to get started. And it helps you kind of understand the different processes that are needed to kind of make a machine learning model work without actually having to code in Python or R, for instance. So one of the first things you do here is you can start with a predefined template, which makes it easier. You can start building from your own. And the first step is almost always it's going to be load in your data. So whether that be import or grab it from an existing URL or storage account, we have that capability. You might want to refine that. So you might want to just select a handful of columns within that data set. We then might want to clean our missing data. Then eventually might want to split that data into our training and test. So then in this case, we're actually going to evaluate two different models here. One being a boosted decision tree regression and one being a decision forest regression. So you initialize those models, you connect it to a training procedure, which connects it to our data. This gives you a trained model. We can then score our test data and then finally evaluate. And so for instance, this has some built-in visualizations. So we went ahead and we trained a couple models. We scored them on our test data. And now we can see here the first model on the left got a coefficient of determination of around 0.919. This one about 0.904 and some other statistics as well. And so now kind of once you go through this typical procedure, and of course we have lots of other machine learning algorithms in here if you'd like. So a handful of classification, we have k-means clustering, and then a few different regressions. So once we're happy with that, if we wanted to say, hey, we've trained our model, we've evaluated it, we think it's ready for deployment, you'd simply actually just select the trained model that you're interested in within the experiment. So actually just click it, and then you'd select, in this case, I've already created a predictive experiment, so it'd say update, but if you haven't already created one, it'll say create. You then click create. What it's going to do is it's actually going to take all the necessary dependency activities for that particular model in this experiment and remove all the unnecessary ones. And then it's going to add in a web service input and web service output. So you're left with something like this. And it's going to automatically do that for you. So it's going to take some of the transformation steps from the raw data, apply those transformations, and then score your model and return that as a web service output. So if you wanted to deploy that, you just simply need to click run once to verify that this does in fact run, and then deploy a web service. Once that's deployed, once you click that, you'll just have to select a compute target for it to be deployed onto, and then you can go here and see your web services. So you can see this one's actually a deployed web service within our visual interface for Azure Machine Learning Service, but this is all backed by our Azure Machine Learning Workspace. So if we wanted to, let's say, go back to the workspace, what do we have here? You would actually see that same deployment that we deployed through the visual interface located here in deployments as well. So it's kind of an easy way for someone without even any background to begin utilizing our machine learning workspace, getting comfortable with kind of where things are saved, how they're saved, the typical steps of a typical machine learning process, and then kind of getting that started. Of course, like I mentioned, there are a little bit of limitations to the number of algorithms, but definitely if you have a simple use case, it's a great starting point. Okay. And that's pretty much all I have for you guys today, unless we have any more questions. Okay, well, thank you everyone for your time. I appreciate everyone listening in. I apologize if there was any issues with the stream cutting in and out or able to read my screen. I can also put my email here into the chat window. And so if you have any follow-up questions or looking for documentation, please feel free to email me and I'll help you as best as I can.
All right, awesome. Thank you so much, Daniel. We really appreciate it. It looks like, were you able to get to the question that's down here in the question panel? I'm not sure if it got raised up in the chat too as well. It says, can we use the language other than Python?
Yeah, I'm answering right now. So at the moment, we have an offering for a command line interface to connect, but other than that, it's only Python, unfortunately. Having said that, we do have a lot of our users who have complained about this. And so it is something our product group is keenly aware of, and we should be rolling out an R SDK somewhere in the new year.
Awesome. Another question is, will this work for object detection in images?
Yeah, absolutely. So all this is it's just a workspace for designing your own models. So absolutely is the question. If the question is automated machine learning for image classification, no, AutoML specializes in typical classification. So it's not going to train like a convolutional neural net, if that's what you're asking. But in terms of just in general, how would you utilize the workspace? You could absolutely build your own object detection algorithm in TensorFlow or Keras and deploy that as a web service within the workspace. Another thing to look at is we also have our Vision API, which is part of our cognitive services that actually offers object detection as a pre-trained model. And then we also have custom Vision API where you can kind of easily train your own custom vision model. But that is outside of the workspace.
Awesome. Let me see if there's another question. That looks like that might be it. I don't think I see anything else. Yep, that looks like that's it. Well, all right, everybody, if that's all the questions, if you guys are looking to get into the next session, just go up and click in your left-hand corner, click the more button, and it will take you to the next session. Daniel, thank you so much for hosting this session. We really appreciate it.
Yeah, thanks everyone for listening. And sorry we started off a little late, but I still think we got through a lot. So thank you.
No problem. I'm sure they got a lot from it. And for those of you who are asking about the recordings are available probably about 5 minutes after this session ends. You just go back to the session and you can just hit the playback on the session that you want to see the recording on. But if you guys have any questions for myself or for Daniel, please feel free to reach out to either one of us. We'll be happy to help. You guys have a wonderful rest of your Azure Data Week, Azure Data Day. Like I said before, click up in the left-hand corner. It will take you to the next session. Thank you again, Daniel. We appreciate it. And you guys have a wonderful day.
Thank you, everyone.